and it is a Herriott-cavity-assisted closed-loop Xenon isotope comagnetometer. Yeah, okay.
Okay.
You're good to go.
Thank you. Hi, everyone. This is Chuanpeng Hao from University of Science and Technology of China. I will report recent progress on a Herriott-cavity-assisted closed-loop Xenon isotope magnetometer. So here is a plot of the Xenon isotope comagnetometer. The reason why we choose nuclear spin for the comagnetometer is that it has long relaxation time and little interference from the environment. We use the pump beam to polarize rubidium atoms, and the Xenon nuclear spin polarization is hyperpolarized. The polarized rubidium atoms can be used as an inside magnetometer to detect the signal of Xenon. And the measure the frequency for each Xenon isotope would be given here. If we do an operation like this, the result is the rotation. This field pioneered by the North Grumman company. There are two research directions in this field, which are miniaturization and high performance. Recently, the work group implemented the Xenon isotope comagnetometer using the new field modulation method. There are some changes in the Xenon isotope comagnetometer, so people are trying different ways to get better performance. An important question is that the sensitivity of the rubidium magnetometer is limited by the line width of the rubidium atoms. Figure compares the spin noise spectrum with and without Xenon. It can tell us that the relaxing of the rubidium atoms is mainly limited by their collision with the Xenon atoms. It will greatly widen the line width of the rubidium atoms. The performance of Xenon isotope comagnetometer is limited by the sensitivity of the rubidium magnetometer, which is inversely proportional to the resonance line width. Nowadays, there are two main ways to improve their sensitivity. One is active and the other is passive. Parametric modulation is one of the common used active methods. Apply a modulation field BC along the direction of the pump beam and the main magnetic field, and detect the first harmonic signal of modulation field. The magnetometer is sensitive to the magnetic field in the XY plane. The magnitude of the modulated field is comparable to the main magnetic field, which potentially affects the system stability. People choose conventional cell most of the time. We want to use the multipass cavity, which helps to increase the signal to noise ratio of the rubidium magnetometer. And we choose a compact Herriott-cavity design. Herriott-cavity is a passive method instead of the parametric modulation. There is a proto difficulty to use multipass cavity. You need to make sure the distance between the two mirrors, the angle of the optical axis, and the other factors are accurate. We standardize the fabrication of the Herriott-cavity cell using the technology of anotic bonding. Anotic bonding is implemented at high temperature and voltage. It binds glass and silicon wafers close. In fact, it's an electrochemical reaction in which silicon and oxygen anions combine to form stable silicon-oxygen bonds. Finally, the glass cover is bonded and filled with atoms. It can be convenient combining the anotic bonding method and the 3D printing technology. We can get rid of the complicated manual optical alignment. We use this kind of cell in our experiment. In this figure, we can know that the closed loop sensitivity of rubidium magnetometer using the Herriott-cavity cell is much better than that of the conventional cell, so our passive method worked. We performed the experiment in a 5-layer biometal shell. The pump beam and the main magnetic field B are in the Z direction, and the probe beam is in the X direction. As mentioned before, together with a 3D printed platform, we can get rid of optical adjustment. The multipass cell contains 3 tau Xenon 129 and 37 tau Xenon 131. Xenon isotope atoms are pumped and probed by polarized rubidium atoms and continuous driving by oscillating magnetic field in the X direction. The part of closed loop operation using phase lock loop is described in the following part. We scan oscillating magnetic field respectively, and then we get these figures. For Xenon 129, the line width is 40 millihertz, and for Xenon 131, the line width is 33 millihertz. The bandwidth of the system in closed loop can far exceed the line width of the Xenon signal in open loop. What's more, the Xenon can work in the maximum signal, so we want our system to work in the closed loop mode. We can see that near the resonant point, there is a linear relationship between the phase of Xenon signal and the frequency of the driving field. From the open loop results there, we choose the center point of the phase response as the set point. The phase signal asks to keep the driving field frequency on resonance through the phase lock loop. The frequency feedback controls the driving field frequency to get the maximum signal. And we also read the frequency feedback signal. Then, when we use our Xenon isotope magnetometer as a gel, the left figure shows the amplitude spectrum density. The reader is Xenon 129, the black is Xenon 131, and the blue is the rotation. The common mode noise can be suppressed well in the low frequency, and the source of this noise may be mainly magnetic field noise. The right figure shows the standard alarm deviation of Xenon 129, Xenon 131, and the rotation. A system is able to get a bias state instability of roughly 0.1 MHz after 1,000 of integration. The system is in a stable of continuous operation, and we can get bias drift like this within plus or minus 0.05 degree in 5,000 period with the closed loop operation. We use this conventional relation to convert the frequency we read from the DIQ to the angle. The left figure shows the demodulated phase and amplitude for rubidium isotope as oscillating magnetic field is scanned, giving a familiar NMR resonance shape. The system can be easily extended to simultaneously working to comagnetometer using a single cell, which include closed loop rubidium isotope comagnetometers and Xenon isotope comagnetometers. The closed loop rubidium isotope comagnetometers and Xenon works in the familiar way. We applied the calibration field in the Z direction. Rubidium 85 and rubidium 87 have the equal response. Meanwhile, Xenon isotope comagnetometer is sensitive to the anomalous coupling with neutral spin, and the rubidium isotope comagnetometer is sensitive to the anomalous coupling with proton spin. And then we are going to design a smaller Herriott-cavity cell and a more compact system, facilitate miniaturization and reduce the effects of magnetic field gradients. So, in conclusion, we use a Herriott-cavity in a Xenon isotope comagnetometer to improve the WOPM magnetometer. This Xenon isotope comagnetometer can reach a virus instability better than 0.2 degree per hour. This comagnetometer can be extended to the dual comagnetometer operation mode, which has vital application in precise measurement, including the numerical experiment. That's all. Thank you.
Thank you very much for your presentation. And once more, the session is open for questions. And we kindly ask you to raise your hand. Like, this is a feature in Zoom where you can just indicate that you have a question.
I can actually
but
not
maybe
raise my hand.
Okay, maybe the hosts cannot do it. So let's say, but I have a question. Otherwise, you can also ask that we unmute you. Like, I have a question. Like this Herriott-cavity, was it done by? Did you do it on your own, or was it in a collaboration?
Sorry.
Like the Herriott-cavity was done by you, or is it a commercial product, or is it a collaboration?
Yes.
Who has done this cavity?
Our group do the analytical bonding and the Herriott-cavity. We can do it ourselves.
Okay, and another question is you had this 3D printed cage, so to say, where everything was in. And the question is a little bit like when you go into the Herriott cell, it goes back and forth, back and forth. So isn't the precision an issue here? That you eventually like if it's only minimal in a wrong position, that you do not hit the exit part anymore?
It is in fact the 3D printing technique has errors, so we just had a little adjustment. Can save a lot of time. The 3D, yes.
Okay. So I think also there are two more questions coming in. It seems that a few people are not able to kind of raise their hand. Maybe the feature is not in all versions just available. And there's a question by Mark Limes. Have you been able to see any dipolar shape effects from the xenon magnetization?
Sorry, I didn't see this phenomenon.
No, the question is in the chat. Like,
yes,
I just repeat the question. And the question is, have you been able to see any dipolar shape effects from the xenon magnetization?
We haven't seen it, and we didn't do some. It didn't do some research in this field, so I'm not sure if it has the Doppler shift in my experiment, because we didn't see this effect in our experiment.
Okay, there was a like maybe just to make it more clear, there was a question by Ricardo, which is here shown on the slide. It was regarding the overall back and forth passes. So like these are totally 22 passes, if I'm correct, and the distance is about like 19.3 millimeters. So it's about 22 times 19.3, correct? The overall optical path length.
We have a camera. We can see the spot in the front mirror or the back mirror. So in this way, we can make sure the reflection times.
Mm-hmm. There's another question coming in from Viktor Lebedev from PTB Berlin. What are the diffusion lengths of rubidium under your conditions? And if the rubidium line is inhomogeneously broadened due to the B0 field gradients?
Yeah, I'm reading the question.
Maybe you can also repeat the question and kind of answer it one-to-one for all of us.
We haven't thought of this question, but we have no clear answer for the question. It's our first experiment in this system, so we didn't have enough evidence for the question.
There's another question coming in from Leibniz IPHT in Jena. Maybe you can also read the question and answer it on the way. Do you see it? On the negative impact on the optical properties of the mirrors due to the sodium shift in the bonding? Chuanpeng, are you still there? Are you reading the question?
Yeah, I'm there. I'm reading the question.
Can you read it for all of us and answer it?
We will design I think.
So the question is twofold. I think, let's say, the first part of the question is regarding the properties of the windows or the mirrors. Is the quality affected by the bonding process?
I will design a mode to make sure the mirrors in the right place. We use a mode to accurate the mirrors in the right place.
Perhaps to clarify my question, Florian Wittkemper here from the Leibniz IPHT. So in the anodic bonding, you have a sodium shift in the glass.
Yes.
So in the end, you will have your bond interface between the silicon and the glass, where you will have a depletion region of the sodium. So the rest of the sodium will be drawn to your electrode here on the top of your glass. So you will have a gradient of different components of the glass, which will have an impact on the refractive index, for example, and the surface properties. For example, the porosity and the side reactions, for example, to sodium acid on the top. So do you observe any negative impacts from this anodic bonding on your mirrors?
Just now we see the background is the gradient will, the magnetic gradient will broaden our line shape of thinner isotopes. That's the background so far we have.
So I think think that we have to cut you off here. I'm a little bit sorry for that. I'm not sure if the last question was actually answered, but we just keep it this way. We thank the speaker once more again, very warmly. Thank you.